السلام عليكم. أساتذتي أساتذة قسم الهندسة المدنية في جامعة بغداد. أقدم لكم مشروعي The Assessment of the Theories for Circular Cylindrical Shell Roof Analysis. And here we see the outlines for my presentation today. First of all is introduction. The shell structures are lightweight construction using shell elements. These elements, typically curved, are assumed to make large structures. Typical applications include the aircraft fuselages, boat hulls, and the roofs of larger buildings. A thin shell is defined as a shell with a thickness which is small compared to its other dimensions, and in which deformations are not large compared to thickness. A primary difference between a shell structure and a plate structure is that in used the unstressed plate, the unstressed state, the shell structure has curvature as opposed to the plate structure which is flat. The thin shells are an example of strength through form as opposed to strength through mass. The effort in design is to make the shell as thin as practical requirements will permit, so that the dead weight is reduced and the structure functions as a membrane free from large bending stresses. By this means, a minimum of materials is used to the maximum structural advantage. In this slide, we see the classification of the shells. We are interested in the singly curved or the developable surfaces, which is the Gaussian curvatures, the Gaussian curvatures, which are classified into three types of the curvature. We have the synclastic, we have the anticlastic, and the doubly curved, but we are more interested in the zero Gauss curvature, and more precisely the circular cylindrical shell. And in this picture we can see the types, some of the types that are considered to be thin shells. The advantages of the shell structures are the shell structures are very interesting due to their impressive strength to weight ratios. They are able to span over large areas while having an exceptionally less thickness. This is primarily due to their form-based structural behavior. The properties mentioned above are highlighted by various shell stresses in existence today. Shells provide a means to obtain an aesthetical and structurally efficient design. They can take several shapes and forms which lie at the mercy of the designer. Coupled with the fact that they take up less materials for construction, shells became increasingly popular in the last several decades. While, on the other side, with the cons or the disadvantages, since the concrete is a porous material, concrete domes often have issues with sealing. If not treated, rainwater can seep through the roof and leak into the interior of the building. On the other hand, the seamless construction of concrete domes prevents air from escaping and can lead to build up of condensation on the inside of the shell. Shingling or sealants are common solutions to the problem of the exterior moisture, and ventilation can address condensation. The stress analysis of the shells. Elastic behavior is usually assumed for shell structural analysis, with a suitable assumption to approximate the stresses that are usually determined by the membrane theory are assumed constant across the shell thickness. The membrane theory for shells, however, neglects the bending stresses, yet every shell is subjected to bending moments not only under unsymmetrical loads, but under uniform and symmetrical loads. In the membrane theory, the shell is idealized as a membrane incapable of resisting bending stresses. An example of a pure membrane state of stress is furnished by a circular pipe subjected to fluid pressure. Shells in practice are of a finite side determined at their edge members. In such shells, it is not possible to maintain a membrane state of equilibrium. On the other hand, in the bending theory, the most reinforced concrete shells in practice do not behave as membranes. Along the edges of the shell, stresses and displacement differ from those given by the membrane theory, which depends on the type of the physical boundary condition that exists along the supporting edges. The stress analysis of the shells in the bending theory may be carried out in three stages. First is the membrane analysis of the surface loads acting on the shell. Two is the bending analysis of the unloaded shells. And in step 3, the superposition of the results 1 and 2 to realize the actual boundary conditions that existing along the straight edges of the wall. In the beam theory developed by the Lundgren the cylindrical shell is analyzed as a beam of curved cross-sections spanning between the end frames or traverses in the case of long shell. The longitudinal force components are predominant and hence the beam theory is ideally suited for the analysis. The beam theory is generally applicable for cylindrical shell with the ratio of L divided by R, which is the radius, exceeding the value of pi. In the beam theory, the cross-section of the shell is assumed with or without edge beam, and the sectional properties is determined, and the stresses are computed using the beam theory. An arch analysis is also conducted to determine the traverse moments and the thrust so that suitable reinforcement is designed. And we can see in this figure the predominant longitudinal forces along the shell and the arch behavior of the curved cross-section. The finite element method is a numerical technique for solving problems which are described by partial differential equations or can be formulated as functional minimization. A domain of interest is represented as an assembly of the finite elements. There are two features for the finite elements are worth to be mentioned: that the piecewise approximation of the physical fields on the finite elements provides good precision with even with simple approximating functions. Increasing the number of elements, we can achieve any precision. Number two is the locality of the approximation leads to sparse equations systems for a discretized problem. This helps to solve problems with very large numbers of nodal unknowns. In this project, we use the StudyPro version 8i software to carry out the finite element analysis. The aim of this study, due to the complexity of the thin shell structures, this project is intended to investigate the theories developed to analyze the cylindrical shell roofs, which are mentioned before, the membrane theory and the beam theory, and we used the finite element to check for these two methods. To achieve this goal, examples related to different typical circular cylindrical shells are investigated herein as follows. The example 1, which relates to a typical interior shell of a multiple group of shells with feather edge beam, for which the L over A is equal to 2, and the example 2, which relates to a typical single short shell without edge beam, for which the L over A is less than 1. Each problem is to investigate the problem analytically and numerically, and the analysis is carried out in 3 steps. Step 1 is the analysis by using the beam theory. Step 2 is by using the finite element. Step 3 is by using the membrane theory. And finally, the discussion of the analysis and for the results. And after that, we can see the example 1. And here is the properties of this example. Here is the picture for the geometric shape. And here we see the results for the beam theory. And in this table, we can see the results of the both membrane and the finite element. In this figure, we can see the results interpreted graphically. The first one is for the membrane force Nx, which is the inner plane stress, and we can see that the beam theory are much more accurate than the membrane theory, which the beam theory resemble the finite element more than the membrane theory. And the results continued for the next membrane force and phi. Likewise, the beam theory gives more accurate and more resembling the finite element results. And this is the bending moment. Finally, move on to the second example, which used these properties. The results in this table for the beam theory and also for the membrane and the finite element results. In the final results graph, we can see that the beam theory and the membrane theory are slightly different, but the membrane theory may be not clear in this in the force, the Nx, but in almost 4 drawings show that the beam theory began to diverge from the finite element, while the membrane theory, although it's simple and gives a result and maybe not that much of accuracy, but in comparison with the finite element, we see that there are maybe there are some similarities between them. And we can see also the beam theory, which does not gives any convergence with the finite element, and on the contrary for the first example. So we can conclude the following. So in a conclusion, we saw the results for our forces using the beam theory and the membrane theory and the finite element. And we can say that the 4 points are the conclusion, which the results indicated that the beam theory for the thin shell is best applicable to long circular cylindrical shells, for which the span over their radius ratio is greater than 1. Good agreement between finite element results and the beam theory for such shells is observed. The assessment study revealed that the beam theory generates poor results when applied to short circular cylindrical shells for which the span over their radius ratio is less than 1. And the finite element results revealed that the membrane theory is the best applicable to short circular cylindrical shells for which beam action vanishes and they behave as an arch. So generally, the study indicates that the beam theory is the best to simulate the behavior of the cylindrical shells compared to the membrane theory. Okay, here is the resources I used to conduct this project. Thank you very much for your attention. I hope you are in a good health.